demo session of ICN 2020. So my name is Diala Naboulsi. I am professor at ETS here in Montreal, and I am chairing this session. So today we will have presentations for 6 posters and 2 demos to present. So similarly to the other sessions in the conference, we will have the presentations that are running here on Zoom, and the questions will be handled over Slack. So if you have any questions, please do not hesitate to share them on the Slack channel. So we're starting with the first presentation. So we have Charalampos Katsis, who is a PhD student at Purdue University, and he will be presenting to us real-time digital signatures for named data networking.
Hello everyone, my name is Charalampos Katsis, and with my colleague Ankush Singla and Dr. Elisa Bertino at Purdue University, we're going to present our work on real-time digital signatures for named data networking. An important requirement when dealing with content distribution is to ensure the content integrity and authenticity. Current designs in NDN systems have adopted the traditional PKI for content authentication. ECDSA and RSA are 2 signature schemes supported by several open source NDN libraries that provide both integrity and provenance protection. A drawback of the existing signature schemes is that they introduce a significant computational overhead, adding a lot of latency to the communication. In real-time applications, it is essential to keep the latency to a minimum to maintain a certain quality of service. Our goal is to provide secure and cost-effective authentication for NDN data packets. We propose the structure-free and compact real-time authentication framework, which enables real-time digital signatures for delay-aware authentication in time-critical networks. SCRA transforms any aggregated signature into signer-efficient signature. It pushes a costly generation operations to an offline phase where the producer will pre-compute all the possible chunk signatures and store them in an in-memory table called gamma. In the online phase, the pre-computed chunk signatures for the generated data packet will be fetched and the aggregated signature will be calculated. We instantiate SCRA CRSA, condensed RSA, in the context of NDN, as it is proven to be both signer and verifier efficient. The producer first chooses 2 parameters L and D such that D times L equals B, where L is the number of chunks the hash is sliced into, D is the number of bits per chunk, and B is the number of bits of the SHA-256 hash output. The message hash will be divided into L equal sized chunks. Then an iterative process of concatenating the chunk index with each value in the interval of 0 to 2 to the power of d minus 1 takes place. Afterwards, we hash and sign each concatenated value with the producer's private key. He needs to do this for all the possible values of each of the L chunks. The producer wire encodes the packet into a buffer and then hashes the encoded message and slices it into L chunks of D bits. Now the producer simply fetches the pre-computed signature from table gamma for each chunk I of the hashed message. Subsequently, the producer computes the packet's aggregated signature S. The verification procedure follows similar steps as the signing and the offline phase. The data packet is wire encoded into a buffer and then hashed. Then, the hash is sliced into L chunks. Afterwards, the chunk index is concatenated with the chunk bits and hashed again. The consumer does this for every one of the L chunks. Then, he uses the producer's public key to verify the data packet's signature. We propose real-time application optimizations. SCRA CRSA performs notably better as more packet signatures are aggregated together. The costly exponentiation occurring at the verification phase happens once every k received data packets. Another approach is a probabilistic signing, where a producer can randomly sign packets and save communication and computational cost. The value of L plays an important role in the performance of our scheme. The choice of L affects the size and the construction time of the gamma table, as well as the signing and the verification times. SCRA is highly parallelizable in all of its 3 phases. We can leverage parallel algorithms or hardware acceleration for even better performance. We carry out two performance evaluation experiments. The first one consists of 10,000 inter-data packet exchanges between consumer and producer. The algorithm aggregates the signature per 100 data packets. The NDN CXX codebase has been used for this experiment. As you can see, the results are very promising. This experiment has been conducted on the NDN RTC video conferencing tool. We had a producer application running for 100 seconds and consumer application running for 50 seconds. We assume that the consumers are not data publishers. Our scheme signs every manifest packet just as the already adopted schemes do. All in all, our scheme can provide reliable message authentication for real-time NDN applications with minimal computation and communication overhead.
Okay, thank you, Charalampos, for the presentation. So we got one question from your Sunny. In a known plaintext attack or chosen plaintext attack, can the attacker recover the signature of each possible chunk so that they are able to produce signatures of any other messages without knowing the key?
Regarding the SCRA CRSA instantiation, this is not possible. So there has been a very recent paper by the actual founder of this framework that one of the instantiations of SCRA has this vulnerability by observing a couple of signatures and then be able to reproduce valid messages. But this is not. This is for lattice-based instantiations of SCRA, not for SCRA CRSA.
Okay, all right, I see. Do we have any other questions for our speaker? Okay, no other questions are popping up. So thank you again, Charalampos. And if there are any other questions, please do not hesitate to post them on the channel. So thank you again, Charalampos.
Of course, thank you so much.
And now we have our second presentation from Peter Kietzmann, who is a PhD student at Hamburg. And he will be presenting to us long-range IoT, is LoRaWAN an option for ICN?
Hi, my name is Peter Kietzmann, and I will present our poster, Long-Range IoT, is LoRaWAN an option for ICN? This is joint work from Dirk, Thomas, Matthias, and me. We started investigating on this topic as a result of different success stories in the past in the field of ICN IoT, for example, ICN LoPAN. Today, we try to answer the question, can LoRa-based communication provide similar opportunities? Let's start with an introduction to LoRa and LoRaWAN. LoRa is a low-power, long-range radio technology, and LoRa is the network architecture on top. It is one of the few systems that defines a complete stack with special network designs independent of IP. The main use nowadays is transmission of sensor data over wide distances to a cloud at minimal battery consumption. LoRaWAN defines three operation modes for constrained end nodes. Class A is purely producer-driven. An end node sends an uplink packet, which can be received by any gateway in reach, and it opens two receive slots afterwards. This mode operates most frugal with battery resources, and is the default deployment choice today. Class C operates similarly, but it leaves the second receive window open. In that way, an end node is receive-able at all times, which causes to high energy costs. Class B allows reception of downlink without preceding uplink and intermittent sleep. This is achieved by opening periodic receive windows. However, Class B is not commonly available on deployed infrastructures. LoRaWAN includes infrastructure nodes. Gateways act as next hops for end nodes and form star topologies. They simply relay packets between end nodes and a central network server. The network server is responsible for packet deduplication and all kinds of routing tasks. Downlink routes are selected based on uplink meta information and address one responsible gateway. The network server pre-calculates schedules to end nodes to avoid wireless interference, and it has to satisfy duty cycle restrictions. A roaming specification describes how globally distributed network servers can interconnect, but still a single network server is chosen to manage end node access. The network server translates data to application servers, which act as user interface. These are often accessed using common application layer APIs, such as HTTP or MQTT. It is worth to say that payloads are encrypted on the application layer between application servers and endnodes. So how can we bring ICN to this technology? The most obvious solution is an application layer relay that translates between ICN and LoRaWAN by protocol conversion or by implementing the application server itself. A similar approach is specified by lightweight M2M protocol to run CoAP request response over LoRaWAN. However, no benefits from an ICN routing system will apply in this scenario. But how about we slightly modify the standard LoRaWAN deployment in order to resemble ICN properties more efficiently? Network servers queue downlink packets, which stresses their change of use as ICN caches. Unfortunately, the network server is centralized, but what if we could decentralize it? For example, if one network server would be deployed on every gateway, the distribution of caches increases redundancy and reduces latency. However, we would rarely improve the constraint node performance by that, and a number of problems remain open. Most dramatically, the media access of LoRaWAN relies on a central network server, which would need a major redesign. Gateways blindly forward packets, which stresses the case for ICN, where origins of data are not relevant. So how about interconnecting gateways and equipping them with FIP, PID, and cache, where the network server remains centralized? In this way, an end node can benefit from in-network caches placed on next-hop gateways that might answer requests without forwarding to the wireless. Conversely, requests might be forwarded redundantly by reaching multiple gateways without hitting a cache, which can actually worsen interference. It still remains open, though, how the centralized scheduling approach and routing interacts with distributed gateways. In both the aforementioned solutions, we ignored that payloads are encrypted in LoRaWAN, which poses a huge challenge to ICN, where names are used for routing on any network node. Implementing LoRaWAN as an ICN requires a change of core security mechanisms. From our investigations, we conclude that LoRaWAN, and especially its centralized media access, conflicts with core ICN principles. We argue for an alternative to run ICN directly on top of LoRa. A decentralized MAC layer should allow all nodes to initiate transmissions. Since the long wireless range is more liable to collisions than personal area networks, the MAC must deal with wireless interference as well as device energy constraints. A native ICN network layer on top of the MAC promises additional advantages. It allows for node-to-node, multi-hop, and mesh communication, which leverages forwarding and caching even on constrained nodes. Additionally, transparent access to the ICN layer allows forwarding by low-pans or infrastructure networks without the need of application layer gateways.
Thank you, Peter, for the presentation. So I have a question. I can see that you are proposing new ideas for the implementation of instead of LoRaWAN. So have you considered any implementations at this level?
Not yet. That's the next step. So this is very initial work, and the next steps will cover how exactly would a MAC layer implementation look like that runs directly below the ICN network layer.
I see. Yes. All right. Thank you. Do we have any other? Yes.
And actually, I'd like to, if anyone has some nice ideas and suggestions, I'd be very happy about that to get some in the Slack.
Great. So if anyone has any thoughts to share with Peter, please do not hesitate them on the Slack channel. Okay, so thank you again, Peter, for the presentation. And now we will go for our third presentation. So we have Pouyan Fotouhi Tehrani from Weizenbaum Institute, and who will be presenting to us on economic, societal, and political aspects in ICN.
Hello, and welcome to this presentation on economic, societal, and political aspects in ICN. My name is Pouyan Fotouhi Tehrani, and I'm going to discuss some non-technical issues that we hold crucial for a successful deployment of ICN on a global scale. ICN, as a paradigm shift in networking, evolves around the idea of named data objects and is based on two basic premises. One, the main purpose of the internet is content distribution, and that users don't care about where the data is coming from, they only care about the content itself. Based on this, ICN introduces three fundamental new bindings. The first one is the binding between an ICN name and its location within the network. Respectively, the network layer is responsible to discover, that is to resolve a name to an instance, and deliver content based on its name, be it from the original producer or any other caching node. The network layer is also responsible in mapping names to actual bits and bytes. And finally, it should be possible to map a name to its authorized owner. We posed the question of respective impacts of these newly introduced bindings and discussed 5 topics. First, names are commodities. If we compare ICN names with domain names, we can imagine that at some point ICN names are also going to become valuable commodities, and as such, we need to cater for fair namespace management and mechanisms to address respective conflicts and disputes. If you're interested in this topic, you can check out our previous work. The second topic is the shift of power within information-centric networks due to shift of responsibilities that has been in the hand of content producers and consumers in host-centric networks. Whereas on the internet, the name owners decide how to map a domain name to actual location of data through DNS. In ICN, the network operators decide how to discover data and where to fetch it. Second, by whitelisting or blacklisting specific names, network operators can decide what contents are allowed to exist on the network, something that is more complicated to realize on the internet through deep packet inspection or similar approaches. And finally, namespace managers can decide which entities are allowed to take part in the network by allocating or denying allocation of namespaces. Trustworthy communication, a topic which is currently addressed mainly on the application layer, has been partly pushed down to the network layer. It remains an open challenge for network operators how to authenticate producers and even consumers without performing resource-heavy cryptographic operations. In addition, trustworthy namespace management requires defining a globally acknowledged trust model and respective infrastructure for which there is no consensus at the moment within the ICN community. The fourth topic, accountability, goes hand in hand with the shift of power in ICN. As network operators and namespace managers are given new responsibilities, they can also be held accountable. Nonetheless, we first need to define the limits of such accountability. Are the operators responsible for discovering and delivering illegal or pirated content? How can ICN operators cater for different, even paradoxical legal imperatives in different countries? For example, the Good Samaritan protection in the US or the Germany's Network Enforcement Act. Finally, namespace managers should implement adequate measures comparable to Registrar Accreditation Agreement as a legal framework for allocation and assignment of ICN names. The last topic might be the most interesting challenge for ICN. Since there is no adequate abstraction of producers and consumers, and the communication is defined only through data names, it is respectively very complicated to realize private communication among a restricted number of producers and consumers. Moreover, specifically in case of human meaningful and expressive names, communication confidentiality is jeopardized as names might reveal information about the content itself. And finally, anonymous communication will be hard to realize as signed data reveals the source of a piece of content. In conclusion, we can assert that people care about data, but they also care about all the topics that we discussed here before ICN can enjoy successful deployment on a global scale. If you have any questions, critique, or just find this topic interesting, don't hesitate to contact me at pft@acm.org. Thank you.
Thank you, Pouyan, for your presentation. So I can see that there's a thread going on the Slack channel. So I noticed that you have also answered some of the comments and questions that you got. Would you like to highlight like something in particular? I can see that the thread is quite long, so maybe I let you share your answers for these questions.
I just want to say that this paper was a short 6 pages paper that we at the end posted as a paper as a poster. So it was really hard to make our points compact. What we talked about here on the chat was about the private communication and how we can realize that on the ICN, and that we need also private local ICN networks beside global wide-scale development of the ICN. The rest is comparing to what is happening in the IP world. I don't want to get into the detail of that, if that's okay.
Okay. Yes, sure. And of course, if you wish, you can continue with the discussions on the Slack channel. Let's give it a few more seconds to see if we have any other questions on the presentation.
This is Marie-José. I will have one. I think what Pouyan, what you raise is essentially the value of information, but I think it's also very much related with everything that's happening in data-centric systems right now, where and big data, data-centric, all the things around AI. So do you think that ICN is different from those, or is essentially in the same trend of this very much value that is changing from, I call it that data moved from being data to being information. And I think data is not that valuable, but information is.
That's a very good point. But I think it's really hard to answer, because in my opinion, ICN is trying to, at least at the beginning, there were talks about replacing the whole IP. So we want to have a huge change in the underlying networks. And the argument that I'm bringing here is, if you want to change the underlying network, you have to go with everything that has been evolved with the IP networks. It's not just about delivering content or information fast. It's about the culture, it's about the power, it's about everything else that comes from that. So getting back to your question, I think like the data centers, AI, or whatever, the information aspect of what is going on at the moment does not really pose a danger for the underlying IP network, whereas ICN does. And if you want to change that, we need to address other things if you want to have the same success of the IP networks. Does that make sense?
Yes, it does. But I would actually claim that there's a lot of other things related to information and data that also creating huge societal impacts, and changing the infrastructure is part of it. But yeah, I get what you're saying. But I would actually think that they're probably all part of a trend where I think the value is almost moving from the infrastructure to what is actually being carried by the infrastructure. And I guess if there's people on this call, on these calls that are from traditional operators, they would probably kill me. But I think I kind of agree. I kind of agree with you. So yes, thank you for the answer.
Thanks.
If I inject something somewhat different, I do not believe ICN would start by thinking about replacing IP. Because like I'm old enough, I watched the 40 years back. When the IP first showed up, the goal was not to replace telecom. That is the outcome, but that's not the original goal. I think history repeats itself. Let's understand what ICN is for. It's not about replacing IP. It's about how to serve applications in a fundamentally better way than TCP/IP can do.
But does that mean that it's going to replace IP because it is much better, or just as the IP did?
IP never tried to kick out the telecom. Telecom went off the stage on its own when more and more application traffic got onto IP.
Okay, thank you.
There's also one question on from Dirk Kutscher. Are you assuming ICN will adopt the DNS namespace for named data object names?
That's a very good question. We had last year a paper that we submitted on ICN 19 in Macau. I don't know the answer to that, but my assumption is if we want to have something globally used by everyone, and we don't want to have the whole policies, the whole organizations around naming, then we can make use of DNS, because DNS is there, ICANN is there, the whole multi-stakeholder, multinational way of doing things, way of managing name is there. So it's a good opportunity to use that. If that's a good idea or not, I cannot answer that. And I cannot definitely say if it's gonna be used for ICN or not. It is a good possibility, in my opinion, at least.
Yes, I see. All right. Thank you, Pouyan, so much for your presentation. And now we will have our fourth presentation by Sanjeev Kochikramani, who is PhD student at Florida International University. And he will talk to us about efficient certificate pool for NDN-based systems.
Hello, everyone. My name is Sanjeev Kaushik-Ramani, and I'm here to present CertColis, which is an efficient certificate pool for NDN-based systems. All of us know that NDN relies on public key signing to ensure integrity and authenticity for all data packets that are fetched in the network. One of the considerations for reliability of such signing is limiting the scope, that is, to ensure what piece of data can be signed by which key, and also the time for which each of these keys can be used to sign the data, which basically determines the requirements of least privilege principle. Traditionally, the PKI-based certificates are issued for relatively long periods of time, which runs into months or in some cases even years. Also, the traditional approaches requires an abundance processing and storage capabilities, because the devices will, or the requester will have to generate multiple public-private key pairs, save the private keys for deriving the certificates, and create multiple CSRs or requests and send them to the certificate issuer in order to receive the certificates. In our case, we were considering the use of IoT devices. Hence, this requirement becomes highly improbable. To eliminate the need for revocation and uphold the least privilege principle, we propose the CertColis certification scheme. According to the scheme, we can potentially create a request for multiple simultaneously valid certificates with the use of a single master key, which is called the caterpillar key in our case. So the device will have to generate just one pair of public-private keys, convert them to something called the caterpillar key, and use that to request for multiple certificates. This scheme is built on the elliptic curve cryptography basis and also upholds forward secrecy. That is, of the certificate pool that we have requested, even the compromise of one of the certificates will not lead to the compromise of the other certificates in the pool. Let's have a look at the workflow or the design in more detail. So each of these devices will generate a public-private key pair and add on some attributes to make it a caterpillar key. So the master caterpillar key is required to be stored, which is the private key has to be stored so that it can derive the certificates that are received from the certificate issuer. So once the caterpillar keys are ready and the device can send this as the request for multiple certificates to the certificate issuing authority. So once the certificate issuing authority receives the caterpillar key, it uses an expansion function to generate something called the cocoon of keys or the cocoon keys. So the size of the cocoon set is based on the application, and the requester knows this as a pre-configured parameter. So the specialized naming convention for the cocoon keys is as shown in the slide. So you have the identity namespace, the key cocoon derived as in the derived values. Once the cocoon keys are generated, a randomly created secret is added to it in order to create the butterfly keys. The responses are then encrypted and aggregated and sent back to the device. The device, on receiving the certificates, will be able to decrypt the message and use the caterpillar private key that was stored in order to derive the butterfly private key and hence the butterfly certificate, and use these certificates to sign the data packets. So this is the overall design of Cert Collies. Paper that submitted the abstract has more details on each of these operations, and you can reach out to us either through email to discuss more about this. Thank you.
Okay, thank you, Sanjeev, for the presentation. So we have one question. Does the device have to store every random secret ever used in generating each butterfly keys?
Well, the answer is no. As I mentioned, the device will have to just store one of the private keys that was created initially. That's the part of the caterpillar key, and this would be used to derive. Yeah, so there's just one random secret key that has to be stored, which basically reduces the amount of storage that's required for the device. And this caterpillar key can be used to derive all the certificates that are requested and received from the certificate issuer.
So we got another question. Are you going to release the library implementing this protocol?
We are actually still in the initial phases of the exploration. So once the implementation is complete, yeah, we plan to release a library implementing this protocol. Sure.
I was also actually about to ask you if so far you have any preliminary evaluation for your work.
Yes, we have a preliminary evaluations, but it was not a part of the 6-page write-up that was submitted. Yeah, but we are still working on more implementation scenarios just to make sure that we are able to perform this. Yeah, thank you.
Yes, and yeah, Alex just mentioned it's actually 2 pages that you submitted for the poster.
Yeah, sorry.
It's even shorter than the 6 pages. Okay, all right. So thank you again, Sanjeev, for your presentation. And now we will have a presentation from Young-Yoon Chin, who is at Freie, and he will talk to us about their paper, Chipmunk Distributed Object Storage for NDN.
Okay, let's get started. I'm Young-Yoon Shin from Freie, South Korea. Today, we are going to talk about Chipmunk, that is a distributed object storage system for NDN. We've got our initial idea from RepoNG and wanted to further improve it to have better scalability and easy of user experience by hiding complexity under the hood. Users want to be able to use storage using only simple names regardless of where they are located. Chipmunks provide a common name that users can easily access. So every participating node has a common prefix as a service name besides its own prefix. The metadata storage system is distributed across the network, taking a DHT style approach with keys as data names. Chipmunk nodes are clustered as ring using consistent hashing. The hash of each NDN name is different from one another, and the hash of the same NDN name is consistent. The metadata node is selected through the hash of NDN name that is chosen by a user. This means that the node responsible for the metadata is determined with the hash value and it is distributed across the network. This allows to find the correct destination without broadcasting or using a centralized systems like DNS. We got a lot of questions about using metadata from reviewers. In fact, it is essential in making a distributed storage service that users don't have to be involved in secure storage space. Chipmunk takes care of it and then maps user-given data name to the file that have been stored somewhere in the repository. Chipmunk is an object storage system consisting of a file and metadata storage. And it is implemented based on RepoNG, so it inherits the overall structure and command sets in RepoNG. The file storage of Chipmunk is based on ext4 file systems. It generates subdirectories and stores data packets using 2 characters from the hash of data name. This approach solves many of the concerns for developers who don't want to inherit the limitations from ACID properties from database systems. We plan to adapt user-friendly methods such as drag and drop or copy and paste. Chipmunk node also provide metadata storage along with the file storage system. The metadata storage is basically a key value store. It provides metadata that is mapped with the result of hashing NDN name requested by the user as the key. This is analogous to a simple yellow page or an NDNS. Let's take a closer look at the behavior and the demo environment. This demonstration shows data insertion and retrieval in the Chipmunk cluster. We will use Chipmunk tools based on RepoNG. We have 6 Chipmunk nodes. Each node have a common prefix /Chipmunk. First, the producer gives a data insertion request like this. NDN put file, and common prefix is shipment, and NDN name is hello, and file. And the chipmunk node, which receives and inserts request, pulls the data through the exchange of interest and data messages and stores it in the file system. Like this, the node stored the data. And a metadata is created, and the node to store the metadata is chosen by a hash calculation of NDN name. So node 2 stored metadata. The request to store the metadata is delivered to the selected metadata storage node. Data consumers do not know which nodes have the data. Therefore, consumers request data using only the NDN name like this. NDN get file and just an NDN name, hello. Then hash of NDN name is used to locate the node where the metadata is stored. The metadata is provided from the key value store from the node that is responsible for the metadata. The data is requested to the node that stores the actual data using the information in the metadata. We are currently changing our prototype to adapt forwarding hints to increase flexibility and make it more efficient. Data producers can create replicas and other nodes after a storage request, like this. The node 2 stores only metadata file, and yeah. It means the same data can be requested to be stored in multiple chipmunk nodes for various purposes, such as increasing availability. Now, the node 2 stored the data. The metadata for NDN name is updated when replication is completed and other nodes. When data consumers request NDN name, metadata is provided like this. NDN get file and NDN name, hello. The metadata received contains a list of nodes that actually store data for NDN name. The consumers can choose one of them and request data. We are planning to use this feature to provide load balance among chipmunk nodes. Basic models such as object storage module, insertion, and retrieve command were carried out in phase 1. Now, we are currently proceeding with phase 2. Thank you very much for listening.
Thank you, Young, for your presentation. So on the chat, you got a couple of questions. First of all, each chipmunk server could advertise chipmunk, but do they also advertise hello? So I let you take the question.
I would probably think that since it's 2 or 3 a.m. in Korea right now, maybe our speaker is not there and the questions will be answered on Slack later.
Yes, actually, it seems one of the authors on the paper is already answering some of the questions on Slack. So I let them continue the discussions then there if they prefer to do that.
Sorry, I'm here.
Oh, okay, great. So yes, we got a couple of questions for you. Regarding your Sunny's question, so each chipmunk server could advertise chipmunk, but do they also advertise hello?
Oh yeah, the producers are besides the hello name, then the chipmunk server name is advertised to routing system by each chipmunk server.
Okay. And another question, if users are to pick among multiple replicates, then how the load balancing is done?
Actually, we are planning to load balance. It's the next page. So we plan to load balance.
Okay, so that's part of the future considerations that you have on your agenda for the second phase. Great. And a question from Susmit. Why ask for metadata and not data directly?
Actually, so many reviewers asked these questions, and we think it's essential in marking a distributed storage service that users don't have to be involved in secure storage space. So chipmunk takes care of it and then maps user-given data name to the file that have been stored somewhere in the repository.
Mm-hmm. Okay, I see. And we got a third question from your Sunny. If the producer needs to be online to advertise hello, then the repo alone cannot serve the data hello as soon as the producer goes offline. Oh, that's rather a comment.
Yeah, that's right. The online.
Mm-hmm. Okay, great. Let's give it a couple of more seconds to see if there are any other questions. Yeah, you got one from, so Lixia added a comment. Yep, so you got one opportunity to further discuss collaborations with Lixia. Okay, great. So thank you again, Young, for your presentation. And now we have the presentation from Nishant Sabarwal and Carlos Santillana. So this is going to be a joint presentation from both who are students at UCLA, and they will be presenting to us their work on NDN Drop, device agnostic file sharing using NDN.
We're Nishant and Carlos here to talk to you about NDN Drop. Apple's AirDrop is a useful feature for sharing files across a wireless medium between Apple devices. Inspired by this, we sought to create a one-hop file sharing system that can share files between any devices. Our vision was a user, say Alice, installs NDN Drop on all her devices, such as her phone, her laptop, and her desktop. Then on each device, she creates a special file sharing folder where she can put local files to be shared. Then from any device, she can list the files of another device's folder and download them. This would all be peer-to-peer over NDN. We wanted to create a system to share files wirelessly without needing access to the greater internet, such as using a cloud intermediary. One key feature we identified was security. The user's file should remain private, which is especially important over a broadcast medium. Also, we don't know which devices will participate ahead of time. Some of Alice's devices are mobile and may go out of range, and she may acquire new ones over time. Devices may not always be on or in range, so the user needs to know which ones are currently available so they can list their files. Each node maintains a neighbor list using a soft state protocol. Current neighbors are listed as well as the time they were last heard from. Each node periodically sends out discover interest to get its neighbors' neighbor lists, so it can learn of new neighbors. It updates its own neighbor list as it hears these interests and evicts idle neighbors.
The consumer needs to know which files are available to download, so they can send an interest packet and receive a list of downloadable files. In order to achieve this, the producer has this NDN Drop directory, which has all the shareable files that it hosts. However, when publishing this directory, it also maintains this list.txt file, which contains the names of all files available within that directory. So then the consumer could send that interest packet and for the list.txt specifically, and then retrieve all the names of the files available. We're able to do this because NDN has the ability to make a naming schema, so each consumer can expect a list.txt on the other side, on the producer side. And we created a bash helper script to watch that directory, the NDN Drop directory, and change list.txt if there's any modifications, additions, or removals. Of course, NDN Drop needs to have the ability to download files. We built upon an NDN tools to download files. However, we modified it so instead of printing the standard out, we just downloads it to a local file. And here's an example of a command, NDN Drop retrieve, and where we have the NDN directory, and it will download that to the local machine.
Okay, great. Thank you for the presentation. Do we have any questions for our speaker? Oh, a problem occurred with the presentation.
Standard out, which just downloads it to a local
Session key to encrypt it in private.
Here's an example of a command. We built upon an NDN tools to download files. However, we modified it so instead of printing the standard out, we just downloads it to a local file. And here's an example of a command, NDN Drop retrieve, and where we have the NDN directory, and it will download that to the local machine.
To encrypt its files. Access control is accomplished by restricting access to these session keys. In the example here, Alice's laptop gets a file for the first time from Alice's phone. The laptop now needs the session key to decrypt it. The laptop sends an interest for the session key, signed with its private key. The phone needs to know the laptop is indeed the laptop and is one of Alice's devices. It verifies the interest by requesting the laptop's certificate, which is the laptop's public key, signed by Alice, who is the trust anchor. The phone now verified the laptop's identity and its authority to view the file. The phone returns the session key, encrypted with the laptop's public key, so no one else can decrypt it.
NDN Drop needs to be able to provide confidentiality for its users, and does this through encryption and decryption. First, the symmetric key pair is given to both NDN Drop list and crypto, where one key encrypts the files before publishing, and then with NDN Drop retrieve, anyone can actually retrieve the files. And then, however, to provide the confidentiality, if someone stranger downloads your files, they don't have the other key to decrypt the file. And this is where crypto comes in. You give it the other key from the symmetric key pair, and it decrypts the files. In this case, list.txt.
And the most obvious benefit, I think, is that naming data translates really well for this application. If you have a local file with your dog, you can just host that local file to your NDN Drop, and it's really easy to see where that file is and make sense of it. And finally, neighbor discovery becomes really simple with NDN thanks to broadcasting.
Okay, so we thank the speakers for the presentation of their work on sharing the files in among personal devices. You got one comment and one question from your Sunny. So first comment, you don't really need to generate list.txt file. You can have a producer serve file list special packets. So would our speakers like to answer this comment?
Sorry, Diala, there is no one connected from them. I was checking their names to put them as co-hosts, but I didn't find them.
Okay. Thank you. Yes, I also tried to contact them on Slack, and none of them seem to be connected there as well. So hopefully when they get the chance to get back to the questions and comments on the Slack channel, so hopefully they will be answering them. So now we will move to the following demo that we have. We got the presentation from Sung-Hyuk Pyun, who is at Electronics and Telecommunications Research Institute. So again, from E3, and he will be presenting to us multi-worker NFD and NFD compatible high-speed NDN forwarder.
Hi, I am Sung-Hyuk Pyun from ETRI Korea. Today, I'm going to present the multi-worker NFD, which is an NFD compatible high-speed NDN forwarder, and demonstrate each performance test. This is a joint work with Jong-Sung Lee, Dong-Myung-Seol, and Nam-Seok-Ko from ETRI. The NFD is the default NDN forwarder in most NDN researches. It is designed for modularity and feature extensibility, but shows quite low forwarding performance. So we analyzed the NFD code and did performance profiling with Intel Vuitune profiler, and identified that the main bottleneck of NFD performance is its single-threaded forwarding architecture. NFD only uses single core for forwarding, even in multi-core CPU systems. So we developed a high-speed NDN forwarder named multi-worker NFD. Multi-worker NFD has multi-threaded forwarding architecture. Its design goals are high-speed forwarding, full compatibility with NFD and NDN applications, and supporting easy porting of any new NDN NFT features. High-speed forwarding is achieved with multiple forwarding workers. For full compatibility and each porting of a new NFT feature, we maintain NFT's forwarding plan architecture as is and support all the management features of NFT with the same API. It is based on NFT 0.7.0. Multilocal NFT has multiple info threads, multiple forwarding worker thread management, and archive manager thread. Archive manager thread is same to NFT is unchanged. Each info thread receives packet from each associated faces and distribute to the forwarding workers based on hash of name prefix of pre-configured lengths. Actually, input thread stores the packet to a buffer and sends the packet buffer pointer and each input face ID to the selected forwarding worker using message queues. Forwarding worker do the all packet processing jobs starting from NDN link protocol handling and finally transmit the packet to the outgoing faces. Forwarding tables such as PIT, CS, FIV, measurement tables are distributed to the all workers, so each worker has only the associated table entries. The number of forwarding workers is configurable. Let's look inside of input thread in detail. One input thread is created for each physical port and launched on the configured core. All faces whose local endpoint is associated to an input port are registered to the I/O service of each input thread. For prefix matching between interest and data, all interest data having the same name prefix of pre-configured lengths are sent to the same forwarding worker. Another information used for packet distribution is the PIT token in the NDN IP header. Forwarding worker encodes the worker ID to the PIT token of transmitted interest. If the peer forwarder supports PIT token, the returned data or NAC has the token of matching interest, then it can be sent to the forwarding worker of matching interest without looking the name prefix. These schemes are adapted from NDN DPDK, which is another multi-thread NDN forwarder. We added a new distribution rule for fragmented large packets. As the first fragment has the name and PI token, the distribution rule is same to the interest and data. For subsequent fragments, input thread store the worker ID of first fragment with its fragment index, which is the identifier of a fragmented packet. Because the subsequent fragments has same fragment index, they can be sent to first fragment's forwarding worker. The management thread is the main thread, and it launches input and forwarding worker threads on the configured cores. It receives and distributes packets from local application faces and internal face. It has all the management features of NFT handled by NFT commands and configuration file. Because the table and statistics are spread to the multiple threads, for the processing logic for each command should be modified, and is under development. Today, we demonstrate the forwarding performance of MWNFT with the NDN package generator server and MWNFT server. The servers are connected with two Tangi ports. For test, we developed the NDN package gen, which is based on DPDK package gen 19.12. It can send a stream of interest with its unique names and return data with the same name to the received interest without NFT. This is the exact matching forwarding test, and interest aggregation and CS hit does not occur. MWNFT server has the Xeon Gold 6242 CPU with 16 cores. FBI size is 10K, and next hops are set to send interest from port 0 to port 1, interest from port 1 to port 0. In this demo, we define the forwarding throughput as the sum of forwarded interest and data throughput. Left graph shows the PPS throughput for various data size when the number of forwarding workers is 10. Because MWNFD allocates 2 additional cores for 2 input threads, this result came from 12 core computing powers. The right graph shows the bandwidth throughput with various number of forwarding workers. We can see that the throughput is saturated at 8 or 10 workers, which is 16.4 gigabps with 8 KB data. This saturation is due to the performance limit of the 2 input cores. If more physical ports are used and the server has the additional cores, the maximum throughput can be linearly increased proportional to the number of ports. In this demo, MWNFD can use about 13 times of NFD throughput. Until now, we have focused on the implementation of multi-thread forwarding architecture of MWNFD. Our future work includes the management feature of developments interacting with the multiple input forwarding worker threads and comparability test with the existing NDN applications. After the compatibility test, we will release the source code of MWNFD. In parallel, we'll try to enhancing some NFD's forwarding logic implementations, such as packet receiving process in the input threads and CS operations. In this demo, we show the multi-core NFD can yield more than 16 gigabits of throughput with 10 workers for 8 KB data. We added the MWNFD section in the NFD configuration file. We assigned core 0 and 2 for input thread, and we assigned 10 forwarding cores. And the previous length for distribution is set to 2. This is the packet chain configuration. The name stream size is 10 mega entry, and the data size is set to 8 KB. So we're learning the NDN packet chain and MWNFD. Start sending the entries. You can see the CPU load of MWNFD is about 1200%, and this means that MWNFD fully utilizes the 12 cores, 2 for input thread, 10 for the worker thread. And the port 0 and 1 is 10G, and this is the RX PPS of port 0 and 1 of packet chain, and the sum of the RX PPS is about 500K PPS. And this is in turn the PPS performance of MWNFD. And this is the RxTX bandwidth of port 0 and 1, and sum of RX bandwidth is about 17 gigabps. This means that the bandwidth throughput of MWNFD is 17 gigabps for 8 KB data. Thank you.
Okay, thank you, Song, for your presentation, and thank you for being present here with us together with Young. You are both in South Korea, and it's 4 a.m. At your side. Over the Slack channel, so you got a few questions. I can see that you answered them except for the last one so far. So I'll let you elaborate more on the aspects that are covered if you wish, and also answer our last question.
Could you say again?
So yes, I mentioned that if you would like to elaborate more on the several comments that you got on the Slack channel. So please do not hesitate to go ahead.
Yeah. Packet distribution rule is sent to NDN-DK, and we distributed the FIB entry to the workers. And so FIB, each worker has only partial FIB entries, and also measurement table and PI table also distribute to the all workers. So each worker has only partial entry related to the they are related to prefixes, FIB prefixes. Yes.
Okay, all right, thank you. And if you wish, so I can see like you answered the last question on the chat. If you wish also to elaborate more on the aspects that you discussed on the Slack channel, you can also go ahead.
Yeah, I think that I said all the answers. Yes, that's it.
Okay, that's it. Perfect. So maybe we'll give it a few more seconds to see if we got any other questions for Sung. Okay, so we will leave any additional questions then for the Slack channel. So if you have any questions to Sung, do not hesitate, please, to post them on the Slack channel. Okay, so thank you again, Song, for your presentation. And last but not least, we have a presentation from George Torres, who is from National Institute of Standards and Technology. And he's with us today, and he will be presenting to us his work on NDN fuzz, stateful structure aware fuzzer for name data networking.
Hello, my name is George Torres. I'm here to present NFT Fuzz, a stateful structure-aware fuzzer for name data networking. I worked on this with my colleagues at the National Institute of Standards and Technology. For those who are not familiar with fuzzers, fuzz testing, or fuzzing, is a software testing technique that aims to automatically find bugs in computer programs. There are various types of fuzzers, each with their own upsides and downsides, but they all follow the same high-level operating principle. That is, the fuzzer generates invalid or unexpected inputs and feeds these inputs to a program under test. This program is then monitored for any errors such as crashes or memory leaks. If an error is found, the input is saved for later analysis and debugging. Fuzzing is especially useful when it's applied to software that implements network protocols or services, because the inputs, which are in this case packets, often come from untrusted users. As a testament to the effectiveness of this technique, the Google-backed OSS Fuzz initiative has so far found over 20,000 bugs in 300 widely used open-source projects. However, fuzz testing has not been applied to NDN yet, and this is why we've developed NFT Fuzz, the first fuzzer for the NDN forwarding daemon NFT. Fuzzing a protocol such as NDN poses some interesting challenges that we had to solve in NFT Fuzz. One of the first challenges we encounter is that NDN's interest in data packets have a highly structured format based on TLVs. Therefore, a naive fuzzer that blindly mutates random bytes in the packet would most likely break the TLV structure and get rejected by NFD's parser. This means that the fuzzer must have a basic understanding of the NDN packet format and structure. So we taught NFT Fuzz how to produce packets that are valid enough to be recognized by the parser, but are also invalid enough as to expose bugs in the forwarding logic. The second challenge we came across is that NDN has a stateful data plane. Therefore, the fuzzer must also be stateful. This has various implications on the design of NFT Fuzz. For instance, we maintain a history of packets that were recently sent to the forwarder. So we can test unique NDN features such as retransmission suppression, intra-data matching, and content caching. We also found out that a single packet is typically insufficient to trigger a bug. So with NFT Fuzz, we extended the input format to represent not just one packet, but a sequence of packets, or a packet trace. Along with multiple packets, we also have to deal with multiple faces. This is because some NDN features such as inter-segregation and forwarding strategies need more than one input or output face to really have all of their logic tested in full. Thus, the fuzzer must maintain these faces and keep track of what face a particular packet was sent through. NFT Fuzz leverages LLVM's libfuzzer as its core fuzzing engine and complements it with a two-level custom mutator. At the top level, we have a packet mutator that understands the NDN protocol semantics and makes decisions on what packet to generate next. Then the top-level mutator calls a lower-level mutator that operates on the TLV structure by randomly adding, removing, or rearranging individual TLV elements, or changing their value. We also instrument NFT and the NDN library with address sanitizer in order to more reliably catch memory errors such as out-of-bounds accesses. And we use Google's flat buffer so that we can efficiently serialize and deserialize the fuzzer's inputs, which are the packet traces plus some metadata, into the corpus, which is then stored on disk. The picture shows a very high-level overview of the main fuzzing loop. So a random input is picked from the corpus past the mutator to be altered and is then fed to NFT. Now, if we're lucky, NFT will crash. That means the fuzzer found a bug, which is then reported to the user for analysis and eventually fixed. But in most cases, NFT will not crash. So the fuzzer will check the code coverage analysis to see if that particular input discovered new execution paths in the code. If that is the case, the input is saved into the corpus so that it can be further mutated in future iterations. This process is repeated until a bug is detected. NFT Fuzz is still a work in progress, but preliminary results are very promising. The fuzzer found 4 bugs in NFT in just a few hours of testing. Future work includes expanding coverage to include NFT management, the NDN link protocol, and NAC. We also want to try other fuzzing engines such as AFO++, Hong Fuzz, and we're looking into investigating a hybrid approach for packet generation and mutation to see if we can expand coverage in a meaningful way. Thank you for your time and attention.
Okay, thank you, George, for the presentation. Do we have any questions for George? So I have a question regarding the granularity of the operations that you are considering. Are you making like operating at the level of each one of the packets that you are receiving, or is it rather like at the reception of more than one packet that you are making the conducting the mutations that you have in the system?
Yeah, so we mutate on a packet level, but we also keep a trace of every packet that we're sending out. So yeah, and we also keep a track of the history of what we're sending so that we can make higher level decisions as well as we proceed through the fuzzing instance.
Okay, thank you. Do we have other questions for George? Okay, so no more questions so far. So if in case anyone has more questions, so please do not hesitate to share them on the Slack channel. And we thank again George for the presentation. And so this ends our session today with our 6 posters and 2 demos. So we thank the speakers, and we thank all people who attended this session.